Somewhere inside galaxies, a star is being born. Gas clouds are collapsing, nuclear fusion is igniting, light is breaking free for the first time in billions of years. But this won't last forever. Every galaxy in the universe is on a journey. Some are young and wild, exploding with newborn stars at rates we can barely imagine. Others have grown old and quiet, their fires dimmed, their fuel exhausted. This galaxy is dead, not destroyed, not gone, but dead in the way astronomers mean it. No new stars are forming here. The nurseries have closed, the lights are going out, one ancient sun at a time. How does a galaxy die? Can it ever come back? And what does this tell us about the fate of our own Milky Way, our own cosmic home spinning through the darkness? Over the next few hours, we're going to follow the life of a galaxy from its violent birth in the early universe to its quiet ending billions of years from now. We'll witness the peak of cosmic history, when the universe was making stars faster than it ever will again. We'll explore the forces that can shut down an entire galaxy, cutting off the very process that gives it life. And we'll discover that galaxy death isn't an explosion or a catastrophe. It's something stranger, slower, and in its own way, more profound. It's the universe growing old. But before we can understand how galaxies die, we need to understand how they're born. And that story begins nearly 14 billion years ago, in the moments after the Big Bang, when the universe was nothing but darkness, hydrogen, and the invisible pull of gravity. This is where it all begins. Chapter 1. What does it mean for a galaxy to die? When we talk about a galaxy dying, we need to be very clear about what we mean. Because galaxies don't die the way stars do. They don't explode. They don't collapse into black holes. They don't vanish from the universe in some catastrophic event. Instead, they fade, slowly, quietly, over billions of years. Think of it this way. A galaxy is not just a collection of stars frozen in space. It's a living ecosystem, a cosmic factory constantly making new stars from raw materials. Gas and dust swirl through its spiral arms. Gravity pulls this material together. When enough gas piles up in one place, it collapses under its own weight, heats up, and ignites nuclear fusion. A star is born. This process has been happening for nearly the entire history of the universe. In our own Milky Way galaxy, new stars are being born right now, at this very moment. About 7 new stars form every single year. That might not sound like much, but multiply that over millions and billions of years, and you're talking about a galaxy that is very much alive, very much active, constantly renewing itself. But what happens when that process stops? What happens when a galaxy runs out of gas, or something prevents that gas from cooling and collapsing into new stars? What happens when the factory shuts down? That's what astronomers call galaxy death. Not the death of the stars that already exist, but the end of star formation itself. No new stars being born, no new light being created, just the slow dimming of ancient suns that have been burning for billions of years, gradually using up their fuel, one by one, fading into darkness. This is the fate that awaits every galaxy in the universe, eventually, including our own. Now, before you start feeling existential dread, let me put this in perspective. The timescales we're talking about here are almost incomprehensible. We're talking about processes that take not millions of years, not even billions of years, but tens of billions, hundreds of billions of years. The universe itself is only 13.8 billion years old. Most galaxies still have plenty of life left in them, but the universe is aging, and we can see the evidence everywhere we look. When astronomers point their telescopes at distant galaxies, they're not just looking across space. They're looking back in time. Light takes time to travel, so when we observe a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago when the universe was only about 4 billion years old. And what we see is astonishing. Those distant ancient galaxies were making stars at rates that would seem almost violent by today's standards. Some of them were forming hundreds, even thousands of new stars every single year. Compare that to our Milky Way's 7 stars per year, and you start to realize something fundamental about the universe. It was more alive in the past than it is now. Star formation across the entire universe peaked about 10 billion years ago, during a period astronomers call cosmic noon. That was when galaxies were at their most active, their most productive, their most alive. Since then, star formation has been declining. Not in every individual galaxy, but on average across the universe as a whole. The universe is past its prime. It's middle-aged, slowly winding down. And when we study dead galaxies, galaxies where star formation has completely shut down, we're studying our own future. We're looking at what the Milky Way might become billions of years from now. So what does a dead galaxy actually look like? Well, it's not dark. That's a common misconception. A dead galaxy is still filled with stars, billions and billions of them. But those stars are old. They're red and yellow, the cooler stars that live for trillions of years. The hot, bright blue stars, the ones that make a galaxy look vibrant and alive, those are short-lived. They burn through their fuel in just a few million years. Without new star formation to replace them, they disappear, and the galaxy's light shifts toward the red end of the spectrum. Dead galaxies also tend to have a very different shape. While living galaxies are often spirals with elegant arms and lanes of dust and gas, dead galaxies are usually elliptical. They're smooth, featureless, shaped like footballs or eggs. There's no structure, no spiral arms, no obvious rotation. Just a blob of old stars slowly orbiting a central, supermassive black hole. And there's very little gas or dust. The raw materials for making stars are gone, either consumed in the formation of existing stars or blown away by some external force. When astronomers look at these galaxies through telescopes, especially through infrared instruments that can detect heat and dust, they see almost nothing. No warm dust, no glowing gas clouds, no nebulae where new stars might form. Just the cold, steady light of ancient stars. This is what death looks like on a galactic scale. But here's where it gets interesting. When you start asking why galaxies die, the answer isn't simple. There isn't just one process that shuts down star formation. There are several, and they can work individually or in combination. Some galaxies die because they simply run out of fuel. Others are killed by their own central black holes. Some are destroyed in violent collisions with other galaxies, and some are stripped of their gas by their environment, by the hot gas that fills the space between galaxies in massive galaxy clusters. Understanding these processes, understanding the many ways a galaxy can die, that's what we're going to explore in the hours ahead. But first, we need to go back to the beginning. We need to see how galaxies are born, how they come to life in the first place. Because you can't understand death without understanding life. You can't appreciate the end of star formation without seeing how star formation begins. So let's rewind the clock. Let's go back nearly 14 billion years to the moments after the Big Bang, when the universe was a hot, dense, expanding sea of energy and matter. Let's watch the first galaxies form. Chapter 2. Birth of Galaxies. In the beginning, there was light, and then there was darkness. This might sound backwards, but it's true. For the first 380,000 years after the Big Bang, the universe was so hot and dense that light couldn't travel freely. Photons were constantly colliding with electrons, scattering in every direction. The universe was opaque, a glowing fog of plasma. But then, as the universe expanded and cooled, something remarkable happened. The temperature dropped enough that electrons could finally combine with atomic nuclei, forming the first neutral atoms. Mostly hydrogen, some helium, and trace amounts of lithium. And suddenly, light was free. It could travel across space without constantly being absorbed and re-emitted. We can still see that light today. It's called the cosmic microwave background, and it's the oldest light in the universe, the afterglow of the Big Bang itself, stretched and redshifted by 13.8 billion years of cosmic expansion. But after that moment, after the universe became transparent, something strange happened. It went dark. All the stars that would eventually light up the cosmos hadn't formed yet. The universe entered what astronomers call the Dark Ages, a period lasting hundreds of millions of years when there was no starlight, no galaxies, nothing but clouds of neutral hydrogen gas drifting through the expanding void. But those clouds weren't perfectly smooth. There were tiny variations in density, tiny ripples in the fabric of space itself, imprinted during the first fraction of a second after the Big Bang. And those tiny variations, those quantum fluctuations stretched to cosmic scales, those were the seeds of everything that would come after. Because where the gas was even slightly denser than average, gravity could start to pull more gas inward. Dense regions attracted more matter, becoming denser still, which made their gravity stronger, which pulled in even more matter. It was a runaway process, a feedback loop that amplified those initial tiny differences into massive structures. And there was something else at work, something invisible. Dark matter. We don't know what dark matter is made of. We've never directly detected a particle of it. But we know it's there because we can see its gravitational effects. It doesn't emit light, it doesn't absorb light, it doesn't interact with normal matter in any way except through gravity. But there's 5 times more dark matter in the universe than ordinary matter, and its gravity is what really drove the formation of the first structures. Dark matter began to clump together first, forming vast halos, gravitational wells that would eventually trap ordinary matter, the hydrogen and helium gas that could actually form stars. If you could see dark matter, if you could watch the universe evolve over its first billion years, you would see an incredible sight. Tendrils and filaments of dark matter spreading across space like a vast cosmic web. Where those filaments intersected, where multiple streams of dark matter converged, massive halos would form, the gravitational seeds of future galaxy clusters. And into those dark matter halos, ordinary gas would fall. As the gas fell inward, it heated up. Gravitational energy converted into thermal energy. The gas began to glow. And in the densest regions, where enough gas had accumulated, something extraordinary happened. The first stars ignited. These weren't stars like our sun. They were monsters, some of them hundreds of times more massive than our sun, burning at incredible temperatures, shining with fierce blue-white light. They lived fast and died young, some of them lasting only a few million years before exploding as supernovae. But those explosions were crucial. They created the first heavy elements, the first carbon and oxygen and iron, elements that didn't exist in the immediate aftermath of the Big Bang. And they injected energy back into the surrounding gas, heating it, stirring it, creating turbulence and shock waves that would trigger the formation of more stars. This was the cosmic dawn, the moment when the universe lit up again, after hundreds of millions of years of darkness. And it happened about 200 million to 400 million years after the Big Bang. The first galaxies were nothing like the grand spirals and ellipticals we see today. They were small, chaotic, irregular blobs of stars and gas, maybe only a few 100 million times the mass of our Sun. For comparison, the Milky Way today has a mass of about 1 trillion times the mass of our Sun. So these early galaxies were tiny by modern standards, but they didn't stay small for long. Gravity kept pulling in more gas from the cosmic web, and galaxies began to find each other, drawn together by their mutual gravitational attraction. When two small galaxies collided, they would merge, forming a larger galaxy. That larger galaxy would then absorb other nearby galaxies, growing bigger and bigger over time. This process is called hierarchical structure formation, and it's how all the galaxies we see today were built. Small structures formed first, then merged to create larger structures, which merged to create even larger structures, and so on, building up the cosmic hierarchy from the bottom up. By about 1 billion years after the Big Bang, recognizable galaxies had formed. They were still smaller than today's galaxies, and they were making stars at prodigious rates. But they had organized themselves into rotating disks with central bulges. The basic architecture of galaxies was in place, and they kept growing, kept merging, kept pulling in fresh gas from the cosmic web and converting it into stars. Now, there's something beautiful about this process that I want you to appreciate. The gas that forms stars doesn't just disappear when a star is born. Stars are not the end point of matter. They're more like recycling centers. When massive stars explode as supernovae, they blast most of their material back into space, now enriched with heavy elements. That gas mixes with the surrounding interstellar medium, the thin gas between the stars. Eventually, it cools, it condenses, and it forms new stars. Those new stars will also eventually die, and the cycle continues. In a healthy living galaxy, there's a constant circulation of matter. Gas falls in from outside. Stars form from that gas. Those stars live and die. Their remnants mix back into the interstellar medium. New stars form from that enriched gas. It's a cosmic ecosystem, constantly renewing itself. And for billions of years, that's exactly what galaxies did. They grew, they merged, they formed stars, they recycled their material. The universe was alive with the light of billions of galaxies, each one a furnace of star formation. But that brings us to a critical moment in cosmic history. About 10 billion years ago, something changed. Chapter 3. The Life of an Active Galaxy. Let me take you on a journey through a living galaxy. Not just any galaxy, but a spiral galaxy in its prime. A galaxy much like our own Milky Way, but several billion years ago when star formation was at its peak. Imagine you're floating in space, far enough away to see the entire galaxy spread out before you. It's a breathtaking sight. Spiral arms curve gracefully outward from a bright central bulge, glowing with the light of billions of stars. But it's not just the stars you notice. There are dark lanes running along the spiral arms, lanes of dust and gas that block the light from stars behind them. Those dark lanes are the key to everything. Let's zoom in. Let's dive down into one of those spiral arms and see what's really happening there. As we descend through the galactic disk, you start to notice structure in that dust and gas. It's not evenly spread out. It's clumped and tangled, forming vast clouds, some of them dozens or even hundreds of light years across. These are molecular clouds, so called because the gas inside them is cold enough and dense enough that individual atoms have bonded together to form molecules. Mostly hydrogen molecules, H2, but also more complex molecules, carbon monoxide, water, ammonia, even organic compounds like methanol and formaldehyde. These molecular clouds are the nurseries where stars are born. But most of the cloud is not making stars. Most of it is just sitting there, cold and dark, at temperatures only a few dozen degrees above absolute zero. It's in a delicate balance. The internal pressure of the gas pushing outward is matched by the cloud's gravity pulling inward. Nothing happens. The cloud just floats through space, stable and unchanging, until something disturbs it. Maybe a nearby star explodes as a supernova, and the shock wave from that explosion slams into the cloud, compressing part of it. Or maybe two clouds collide, driven together by the turbulent motions of gas in the galactic disk. Or maybe a spiral density wave, the gravitational pattern that creates the spiral arms themselves, compresses the gas as it passes through. Whatever the trigger, part of the cloud suddenly finds itself compressed, denser than before. And now gravity has the upper hand. That dense clump begins to collapse, pulling in more gas from the surrounding cloud. As it collapses, it fragments into smaller pieces, each one collapsing independently. What started as a single disturbance now becomes dozens or hundreds of separate collapse sites scattered throughout the cloud. Each collapsing fragment heats up as it falls inward. Gravitational potential energy converts to thermal energy. The temperature rises from 10 degrees above absolute zero to hundreds of degrees, then thousands of degrees, then tens of thousands of degrees. At the very center of the collapsing fragment, where the density is highest and the temperature is greatest, hydrogen atoms are moving so fast, colliding with so much energy, that they start to fuse together. 4 hydrogen nuclei combine to form one helium nucleus, releasing a burst of energy in the process. This is nuclear fusion, the same process that powers the sun, the same process that powers every star in the universe. A star is born, but it doesn't stop there. The energy released by fusion creates an outward pressure that stops the collapse. The star reaches an equilibrium with the inward pull of gravity exactly balanced by the outward push of radiation pressure. It settles onto what astronomers call the main sequence, the long, stable phase of a star's life where it will spend the next millions or billions of years steadily fusing hydrogen into helium. And it's not alone. Remember, the original collapsing cloud fragmented into many pieces. What emerges from a molecular cloud is not a single star, but a cluster, sometimes hundreds or thousands of stars, all born together, all emerging into view as the remaining gas and dust is blown away by stellar winds and radiation. These young star clusters are spectacular. The most massive stars, the hot blue giants, shine with incredible luminosity, pumping out ultraviolet radiation that ionizes the surrounding gas, causing it to glow in vivid reds and blues. These glowing regions are called H2 regions, or emission nebulae. The Orion Nebula is a perfect example, one of the closest star-forming regions to Earth, only about 1,300 light-years away. But here's something fascinating. The most massive stars, the ones that shine the brightest, are also the ones that die the fastest. A star 100 times the mass of the Sun might only live for 2 or 3 million years. Compare that to the Sun, which will live for about 10 billion years total, or a small red dwarf star, which could live for trillions of years. Why the difference? It comes down to fuel consumption. Massive stars have more fuel, yes, but they also burn through it at a much faster rate. The core temperature of a massive star is much higher than in a low-mass star, and fusion reactions are extremely sensitive to temperature. A small increase in temperature leads to a huge increase in fusion rate. So massive stars burn bright and die young, while small stars burn dim and live practically forever. When those massive stars finally exhaust their fuel, they don't fade quietly. They explode. A supernova is one of the most violent events in the universe. In a fraction of a second, the core of the star collapses into a neutron star or black hole, releasing more energy than the star emitted during its entire life. The outer layers are blasted into space at speeds of tens of thousands of kilometers per second, carrying with them all the heavy elements forged in the star's core during its life and in the moments of the explosion itself. That material slams into the surrounding interstellar medium, creating an expanding shell of hot gas and triggering new waves of star formation in nearby molecular clouds. The cycle continues. Old stars die, enriching the galaxy with heavy elements. That enriched material eventually collapses to form new stars, which will themselves die and contribute more heavy elements. Generation after generation of stars, each one slightly more metal-rich than the last. By the way, when astronomers talk about metals, they mean any element heavier than hydrogen and helium. So carbon is a metal, oxygen is a metal, even though we wouldn't normally think of them that way. It's just convenient terminology. Now zoom back out. Pull away from that single star-forming region and look at the galaxy as a whole again. The spiral arms are dotted with these bright blue regions, young star clusters and emission nebulae marking where star formation is currently active. Between the spiral arms, the light is more yellowish, dominated by older stars. The central bulge glows with a warm orange light, packed with ancient stars that formed early in the galaxy's history. And if you could see in other wavelengths beyond visible light, you'd see even more. In infrared light, which is sensitive to heat and dust, the spiral arms light up brilliantly. All that dust, warmed by starlight, glows in the infrared. Radio telescopes would show you the cold molecular gas, tracing out the densest regions where stars are about to form. X-ray telescopes would reveal the hot gas from supernova remnants and the intense radiation from the accretion disk around the central supermassive black hole. Yes, there's a supermassive black hole at the center. Nearly every large galaxy has one. The Milky Way's central black hole, called Sagittarius, a star, has a mass of about 4 million times the mass of the Sun. That sounds like a lot, but it's actually tiny compared to the total mass of the galaxy. It's just a tiny fraction of 1%. But it has an enormous influence on its surroundings, as we'll see later when we talk about how black holes can kill galaxies. For now, the important thing to understand is that this galaxy, this spiral galaxy in its prime, is a thriving ecosystem. Gas flows in from outside, falls into the disk, forms stars, gets recycled by supernovae, and forms new stars. It's self-sustaining, self-renewing, a cosmic factory in full production. This is what life looks like on a galactic scale. And about 10 billion years ago, at a time astronomers call cosmic noon, galaxies across the universe were at their most alive. Star formation was at its peak. The universe was making stars faster than it ever had before or ever would again. Let's talk about that remarkable moment in cosmic history. Chapter 4. The Peak of Star Formation. There's a graph that astronomers love to show. On the horizontal axis is time, from the Big Bang to the present day. On the vertical axis is the cosmic star formation rate, the average rate at which the entire universe is converting gas into stars, measured in solar masses per year per cubic megaparsec. Don't worry about the units. The shape of the curve is what matters. It starts near zero, obviously, because right after the Big Bang there weren't any stars yet. It rises rapidly during the first billion years as the first galaxies form and light up the universe. It keeps rising for several billion years more, reaching a peak about 10 to 11 billion years ago. And then it starts to decline. slowly at first, then more steadily. By the time you reach the present day, 13.8 billion years after the Big Bang, the cosmic star formation rate has dropped to only about 1/10 of its peak value. Think about what that means. The universe today is making stars at only 10% of the rate it was making them 10 billion years ago. Star formation hasn't stopped, not by any means. There are still plenty of active galaxies out there, including our own Milky Way. But on average, across the entire universe, star formation is in decline. We're living in a quieter universe than the one that existed in the past. That peak in the star formation rate, that maximum about 10 billion years ago, that's what astronomers call cosmic noon. It's a poetic name for a very real phenomenon. If the history of the universe is like a single day, then cosmic noon was the moment of maximum activity, maximum brightness, maximum life. And we've been sliding into the cosmic afternoon and evening ever since. Now, why did this peak happen when it did? What made 10 billion years ago so special? The answer has to do with the competing processes that drive galaxy evolution. On one hand, you have gas flowing into galaxies from the cosmic web, providing the raw material for star formation. On the other hand, you have processes that heat the gas, eject it from galaxies, or prevent it from cooling and collapsing into stars. In the early universe, the first process dominated. There was a lot of cold gas available, and it was falling into galaxies rapidly. Galaxies were small and still growing through mergers. When two gas-rich galaxies collided, the collision would compress the gas and trigger intense bursts of star formation. These starburst galaxies could form hundreds or even thousands of new stars per year, far more than a typical galaxy today. But over time, several things changed. First, the rate of gas infall slowed down. The cosmic web is a finite resource. As more and more gas got locked up in galaxies and converted into stars, there was less and less free gas available in the space between galaxies. Second, galaxies got better at blowing out their own gas. As star formation increased, so did the number of supernovae. All those exploding stars pumped energy into the interstellar medium, heating the gas and creating powerful winds that could drive material out of the galaxy entirely. This is called stellar feedback, and it's one of the most important processes regulating star formation. Third, the supermassive black holes at the centers of galaxies became more active. As they grew larger and accreted more matter, they released more energy, and that energy could heat the surrounding gas or even blast it out of the galaxy in powerful jets. This is called active galactic nucleus feedback, or AGN feedback, and it's one of the primary mechanisms for shutting down star formation entirely. Fourth, galaxies started to cluster together more. In the early universe, galaxies were more spread out, more isolated. But over time, gravity pulled them together into groups and clusters. And the space between galaxies in a cluster is filled with hot gas, millions of degrees hot, heated by the gravitational energy of the cluster itself. When a galaxy falls into a cluster, that hot intracluster gas can strip away the galaxy's own cold gas, cutting off the supply of star-forming material. All of these processes were at work throughout cosmic history, but their relative importance changed over time. And around 10 billion years ago, the balance tipped. The processes that shut down star formation started to win out over the processes that supply fresh gas. Cosmic noon was the moment of balance, the peak of the curve, the point where the universe transitioned from growing and vibrant to slowly winding down. Now, when we look at galaxies from that era, the galaxies that existed 10 billion years ago, what do we see? We see incredible diversity. Some galaxies were massive spirals, not unlike the Milky Way today, but forming stars at 10 or 20 times the rate. Others were compact starbursts, small but incredibly bright, forming stars at rates of hundreds per year. Some were already beginning to quench, their star formation shutting down as their gas supply was cut off. And some were colliding, locked in gravitational embrace with neighboring galaxies, their gas clouds slamming together and igniting in brilliant starbursts. One of the most famous images in all of astronomy comes from this era. It's called the Hubble Ultra Deep Field. Astronomers pointed the Hubble Space Telescope at a tiny patch of apparently empty sky, a region so small it would be covered by the head of a pin held at arm's length. They left the shutter open, collecting light for over 11 days of exposure time. And in that tiny patch of sky, they found nearly 10,000 galaxies. Most of them were distant, ancient galaxies, their light traveling for billions of years to reach us. Many of them dated from the cosmic noon era, showing us what the universe looked like at its peak. And what we learn from that image, and from countless other deep surveys since then, is that every era of cosmic history has its own character. The early universe was wild and chaotic, with small, irregular galaxies merging and colliding constantly. Cosmic noon was the era of grand spirals and intense starbursts, maximum star formation, maximum activity. And the modern universe is increasingly dominated by large, mature galaxies, many of them ellipticals, many of them already quenched. The universe is aging, and the galaxies are aging with it. But here's what's truly remarkable. We're not just passively observing this process. We're actually trying to understand it, to figure out the physical mechanisms that drive galaxy evolution, to predict what will happen in the future. And that means we need to understand how galaxies die. We need to understand all the different ways that star formation can be shut down. So let's dive into the science of galaxy death. Let's explore the mechanisms, one by one, that can turn a vibrant star-forming galaxy into a red and dead elliptical. Chapter 5. How Galaxies Die. Part 1. Running out of gas. The most obvious way for a galaxy to stop forming stars is simply to run out of gas. This might sound simple, but it's actually more subtle than you might think. Because galaxies don't just have a fixed supply of gas that gets slowly used up. Gas is constantly flowing in and out. It falls in from the cosmic web. It gets converted into stars. It gets blown back out by supernovae and stellar winds. Some of it falls back in. Some escapes entirely. A galaxy is not a closed system. It's more like a leaky bucket that's also constantly being refilled. So when we talk about a galaxy running out of gas, what we really mean is that the inflow of fresh gas has slowed or stopped, and the outflow of gas through stellar winds and supernova has carried away more gas than remains available for star formation. Let me walk you through how this actually happens. Start with the typical spiral galaxy, roughly the size of the Milky Way. Its disk contains about 10 billion solar masses of gas, mostly hydrogen. That sounds like a lot, and it is, but remember that this galaxy is also forming stars at a rate of, let's say, 10 solar masses per year. If you divide the total gas mass by the star formation rate, you get what's called the gas depletion time. It's the amount of time it would take to convert all the available gas into stars if the star formation rate stayed constant and no new gas flowed in. For our example galaxy, that's 10 billion solar masses divided by 10 solar masses per year, which equals 1 billion years. Now, a billion years is a long time. It's enough time for the Sun to orbit the center of the Milky Way about 4 times. But on cosmic timescales, it's not that long. The universe is nearly 14 billion years old. Many galaxies have been around for 10 billion years or more. So, if galaxies are constantly using up their gas on timescales of only a billion years or so, why haven't they all run out by now? Why are galaxies like the Milky Way still forming stars? The answer is that they're being resupplied. Gas is flowing in from outside. In the modern universe, this inflow comes primarily from what astronomers call the circumgalactic medium, or CGM. This is a vast halo of gas surrounding every galaxy, extending out to distances of hundreds of thousands of light years. The CGM is thin, much thinner than the interstellar medium inside the galaxy, but it's enormous in volume, and it contains a significant amount of mass. This gas is slowly cooling and falling inward, pulled by the galaxy's gravity. It doesn't fall straight in. It has some angular momentum, some rotation, so it spirals inward, eventually joining the disk and becoming part of the reservoir of gas available for star formation. As long as this inflow continues, the galaxy can keep forming stars indefinitely. The inflow replenishes the gas reservoir at roughly the same rate that star formation depletes it. It's a steady state, a balance. But what if something disrupts that balance? One possibility is that the inflow simply slows down over time. Remember, the inflow comes from the cosmic web, from the large-scale structure of the universe. In the early universe, those cosmic web filaments were rich with gas. But as galaxies grew and consumed more and more gas, the filaments were depleted. By the present day, there's much less gas left in the cosmic web to accrete, so galaxies today are receiving less inflow than galaxies in the past. And if the inflow rate drops below the star formation rate, the gas reservoir starts to shrink. Another possibility is that something prevents the gas from cooling and falling in. If the gas in the circumgalactic medium is too hot, it can't collapse and form stars. It just sits there, a hot, diffuse halo, gravitationally bound to the galaxy, but not participating in star formation. What could heat the gas that much? Several things. Supernovae and stellar winds from massive stars can inject energy into the circumgalactic medium. That energy heats the gas and can even drive it outward in what astronomers call a galactic wind. But there's an even more powerful source of heating, and it comes from the very center of the galaxy. The supermassive black hole. We'll talk about black hole feedback in more detail in a moment, but for now, just understand that active supermassive black holes can release enormous amounts of energy. That energy propagates outward through the galaxy and into the circumgalactic medium, heating the gas to temperatures of millions of degrees. At those temperatures, the gas cannot cool and collapse on any reasonable timescale. It's effectively shut off from star formation. So even if there's plenty of gas present, even if the total mass of gas in and around the galaxy is huge, if that gas is too hot, it doesn't matter. Stars can't form from hot gas. This is one of the key insights of modern galaxy evolution research. It's not just the amount of gas that matters, it's the state of that gas. Is it cold or hot? Is it dense or diffuse? Is it in the disk where stars can form, or is it in the halo where it's effectively inaccessible? Now, there's one more way that galaxies can lose their gas, and it's more dramatic. They can blow it out entirely. This happens in what are called superwinds or galactic winds. When star formation is extremely intense, when you're forming hundreds of stars per year in a compact region, the combined effect of all those supernovae and stellar winds creates an enormous amount of pressure. The hot gas, heated to millions of degrees by the supernova shocks, expands outward in all directions. If the galaxy's gravity isn't strong enough to hold it back, that gas can escape entirely, flowing out of the galaxy and into intergalactic space. Once the gas leaves the galaxy, it's gone. It won't come back. The galaxy has lost that material forever, unless it somehow manages to accrete fresh gas from outside. Superwinds are particularly common in starburst galaxies, those compact, intensely star-forming systems we see in the early universe and in merging galaxies. They form stars so rapidly that they essentially blow themselves apart, ejecting much of their gas in massive outflows. These galaxies don't die slowly. They die in a blaze of glory, forming stars at unsustainable rates until they expel all their gas and shut down completely. When astronomers observe nearby starburst galaxies, they can actually see these outflows directly. Hot gas streaming out from the galaxy's disk, detected through X-ray emission or through spectroscopy that shows the gas is moving at speeds of hundreds or even thousands of kilometers per second. These are winds of cosmic proportions, carrying away entire solar systems worth of material every single year. And the end result is a galaxy with little or no cold gas left. Star formation drops to near zero. The galaxy fades from blue to red as the short-lived massive stars die off and only the long-lived low-mass stars remain. The galaxy has run out of fuel. It has quenched. But running out of gas is only one way to kill a galaxy. And in many cases, it's not the primary cause. The primary cause, especially for the most massive galaxies, has to do with what's lurking at the center, the supermassive black hole. How galaxies die. Part 2, Black Hole Feedback. At the center of nearly every large galaxy in the universe sits a supermassive black hole. Not a stellar mass black hole, the kind that forms when a massive star collapses. Those are only a few times to a few tens of times the mass of the Sun. We're talking about black holes with masses of millions, even billions of times the mass of the Sun. Our own Milky Way has one. It's called Sagittarius, a star, and it has a mass of about 4 million solar masses. The nearby Andromeda Galaxy has one that's about 50 times more massive, around 200 million solar masses. And some galaxies have absolute monsters, black holes with masses exceeding 10 billion solar masses. How did these things get so big? That's still an active area of research, but the basic idea is that they grew through a combination of gas accretion and mergers. A seed black hole forms in the early universe, maybe from the collapse of a massive star, or maybe from the direct collapse of a dense gas cloud. That black hole sits at the center of a small galaxy and starts accreting gas from its surroundings. As it accretes, it grows. When its host galaxy merges with another galaxy, the two black holes eventually sink to the center and merge as well, creating an even larger black hole. Over billions of years, this process can build up supermassive black holes from relatively small seeds. But here's the thing. When a black hole accretes matter, it doesn't do so quietly. As gas spirals inward toward the black hole, it forms what's called an accretion disk, a swirling disk of material orbiting at tremendous speeds. Friction within the disk heats the gas to millions of degrees, hot enough to emit X-rays. Some of that energy radiates away into space, but not all of it. Some of it gets channeled into powerful jets that shoot out from the poles of the black hole at nearly the speed of light. These jets are among the most powerful phenomena in the universe. They can extend for millions of light years, punching through the galaxy and out into intergalactic space. The energy carried by these jets is staggering, sometimes equivalent to the total energy output of trillions of suns. And all that energy has to go somewhere. Much of it ends up heating the gas in and around the galaxy. The jets plow through the interstellar medium, creating shock waves and turbulence. The radiation from the accretion disk heats the gas directly. The combined effect can raise the temperature of the gas to millions or even tens of millions of degrees. And here's the critical point. Hot gas cannot collapse to form stars. Star formation requires cold gas, gas that's only a few tens of degrees above absolute zero. If you heat the gas to millions of degrees, it expands. It puffs up. The pressure becomes too high for gravity to overcome. Instead of collapsing into dense clouds where stars can form, the gas just sits there, hot and diffuse, doing nothing. This is called AGN feedback, active galactic nucleus feedback, and it's one of the most important processes in all of galaxy evolution. When a supermassive black hole is actively accreting gas, we say the galaxy hosts an active galactic nucleus, or AGN. The AGN pumps energy into the surrounding gas, preventing it from cooling and forming stars. If the AGN is powerful enough, it can effectively shut down star formation across the entire galaxy. And here's the beautiful irony. The black hole needs gas to accrete in order to be active. But by being active, it heats the gas and prevents more gas from falling in. So AGN feedback is self-regulating. The black hole eats until it's full, then it burps out so much energy that it stops more food from arriving. Eventually, the accretion slows down. The AGN becomes less active. The energy output drops. The gas starts to cool again, and star formation can resume. But in massive galaxies, especially in galaxy clusters, the AGN can maintain a long-term balance. It doesn't shut off completely. It stays active at a low level, constantly injecting just enough energy to keep the gas hot and prevent star formation, but not so much energy that it blows all the gas away. Astronomers have observed this process in action in nearby galaxy clusters. The Virgo cluster, the Coma cluster, the Perseus cluster, all of them show evidence of AGN feedback. Radio telescopes reveal the jets from the central black holes, punching cavities in the hot intra-cluster gas. X-ray telescopes show the hot gas surrounding the galaxy with temperatures of tens of millions of degrees. And optical telescopes show that these central galaxies have very little star formation. They're red and dead, despite sitting in environments rich with gas. Without AGN feedback, those galaxies should be forming stars at rates of hundreds of solar masses per year, given how much hot gas surrounds them. But they're not. Star formation is almost completely shut down. The black hole is keeping them dead. Now, AGN feedback comes in different flavors. Astronomers distinguish between what they call quasar mode feedback and radio mode feedback. Quasar mode, also called radiative mode or wind mode, is what happens when the black hole is accreting very rapidly, close to its maximum possible rate. This is called the Eddington limit, and it's determined by the balance between the inward pull of gravity and the outward push of radiation pressure. When a black hole is accreting at the Eddington limit, it's shining as brightly as it possibly can for its mass. These are the quasars, the most luminous objects in the universe. A single quasar can outshine an entire galaxy. And the energy released doesn't just radiate away harmlessly. It drives powerful winds, sometimes at speeds of 10% the speed of light, that slam into the surrounding gas and blow it out of the galaxy entirely. Quasar mode feedback is fast and violent. It can shut down star formation in a matter of tens of millions of years, almost instantly on cosmic timescales. Radio mode feedback, on the other hand, is gentler but more sustained. This is what happens when the black hole is accreting at a lower rate, well below the Eddington limit. Instead of shining brightly and driving winds, the black hole launches jets. Those jets inflate huge bubbles in the surrounding gas, cavities that can be millions of light years across. The jets don't blow the gas away. They just heat it, keeping it too hot to form stars, but not ejecting it entirely. Radio mode feedback is the maintenance mode, the thermostat that keeps massive galaxies quenched over billions of years. So, which type of feedback is more important? It depends on the galaxy and the epoch of cosmic history. In the early universe, during cosmic noon, quasar mode feedback was probably dominant. Black holes were growing rapidly, accreting at high rates, shining as quasars and blowing out gas in massive winds. This may have been the primary mechanism that shut down star formation in the first massive galaxies. In the modern universe, radio mode feedback is more important, especially in galaxy clusters. The black holes have already grown to enormous sizes, and they're now in maintenance mode, keeping the gas hot and preventing new star formation, but not necessarily driving large-scale outflows. There's actually a remarkable correlation that supports this picture. Astronomers have found that the mass of the supermassive black hole at the center of a galaxy is tightly correlated with the mass of the galaxy's bulge, the central concentration of stars. The black hole mass is typically about 1/5 of 1% of the bulge mass. This correlation holds across a huge range of galaxy masses, from small galaxies with black holes of only 1 million solar masses to giant ellipticals with black holes of 10 billion solar masses. Why does this correlation exist? Because the growth of the black hole and the growth of the galaxy are intimately connected through AGN feedback. When the galaxy is young and growing rapidly, both the stars and the black hole are forming from the available gas. But as the black hole grows larger, its feedback becomes more powerful. Eventually, it becomes strong enough to shut down star formation. The galaxy stops growing, the black hole stops growing. They've reached a balance. The fact that this balance occurs at roughly the same ratio for all galaxies, regardless of their size, suggests that AGN feedback is a fundamental process in galaxy evolution. It's not just one mechanism among many. It's a key regulator, a cosmic thermostat that determines when galaxies stop forming stars. But black holes aren't the only thing that can kill a galaxy. Sometimes the culprit is external. Sometimes a galaxy dies because of what's happening around it. How galaxies die. Part 3. Galaxy mergers. When two galaxies collide, it's not like two solid objects smashing together. Galaxies are mostly empty space. The stars are so far apart that they almost never actually collide with each other. If you were standing on a planet in one of those galaxies watching the merger happen, you might not even notice anything unusual for millions of years. But the gas does collide, and that makes all the difference. When two galaxies approach each other, drawn together by gravity, their gas clouds slam together at speeds of hundreds of kilometers per second. That collision creates enormous shock waves that compress the gas, heating it and triggering intense bursts of star formation. For a brief period, the merging system can light up like a cosmic firework. Star formation rates can jump to hundreds or even thousands of times the normal rate. The galaxies become what astronomers call starbursts, some of the brightest objects in the universe. But this burst of star formation comes at a cost. The gas is being consumed at an unsustainable rate. Within a few tens of millions of years, most of the available gas has been converted into stars. And remember all those massive stars we talked about earlier, the ones that die as supernovae after only a few million years? In a starburst, you have thousands of those stars all forming at once. The result is an explosion of supernovae, hundreds or thousands happening every year. The combined effect of all those supernovae creates a superwind, a massive outflow of hot gas that blows away whatever gas wasn't converted into stars. By the time the merger is complete, most of the gas is gone. Either it's been turned into stars, or it's been ejected in the superwind. What's left is a galaxy with very little cold gas, and therefore very little ability to form new stars. The merger has killed both galaxies. But the story doesn't end there. The stars from both galaxies are still there, and they're now orbiting in this new merged system. Without the gas to maintain a nice, flat, rotating disk, those stars settle into a more random, elliptical distribution. This is how elliptical galaxies form. Ellipticals are not separate creations. They're not a different type of galaxy that formed differently from the beginning. They're the end products of galaxy mergers, the fossils of violent collisions that happened billions of years ago. When you look at a giant elliptical galaxy, smooth and featureless and red, you're looking at the aftermath of a merger, or more often, multiple mergers. The individual spiral galaxies that came together to form it are long gone, their disks disrupted and destroyed, their gas consumed or ejected, their stars mixed together into a single massive system. And elliptical galaxies don't form stars. They have very little gas, very little dust, and star formation rates close to zero. They're dead in the astronomical sense. Now, not all galaxy mergers result in complete quenching. It depends on the masses of the galaxies involved and how much gas they have when they collide. If two small gas-poor galaxies merge, you might just end up with a slightly larger gas-poor galaxy. Star formation might be mildly enhanced during the merger, but it won't be a dramatic starburst, and the end result might still have some residual star formation. If one galaxy is much larger than the other, the smaller galaxy might just be absorbed or cannibalized by the larger one. The Milky Way is actually in the process of cannibalizing several small satellite galaxies right now, including the Sagittarius dwarf elliptical galaxy. These minor mergers can add stars and gas to the larger galaxy, but they don't fundamentally change its structure or shut down its star formation. The most dramatic effects happen when two large gas-rich galaxies of similar mass collide. Those are the mergers that create the most intense starbursts, eject the most gas, and result in the most complete quenching. And there's one more important consequence of major mergers. The supermassive black holes at the centers of both galaxies eventually sink to the center of the merged system and merge themselves. When that happens, they release gravitational waves, ripples in space-time itself, carrying away energy and momentum. The merged black hole that forms is often more massive than the sum of the two original black holes, because they've also accreted a lot of gas during the merger process. And that merged black hole, now sitting at the center of a gas-rich post-merger system, can become an extremely powerful AGN, pumping out energy and quenching any remaining star formation. So galaxy mergers can shut down star formation through two complementary mechanisms. First, the starburst consumes and ejects most of the gas. Second, the merger triggers strong AGN activity that heats whatever gas remains. It's a 1-2 punch that can completely quench a galaxy. Now, how common are galaxy mergers? It depends on the environment and the epoch of cosmic history. In the early universe, galaxies were smaller and closer together. Mergers were extremely common. Nearly every galaxy we see at high redshift, meaning great distance and early cosmic time, shows some evidence of interaction or disturbance. The early universe was a chaotic place, with constant mergers building up larger and larger systems through hierarchical assembly. In the modern universe, major mergers are less common, but they still happen. The Milky Way and Andromeda are on a collision course, due to merge in about 4 to 5 billion years. When that happens, both galaxies will likely undergo a burst of star formation, followed by quenching. The result will be a giant elliptical galaxy, sometimes called Milky Way. But even in the modern universe, there are places where mergers are still common. Galaxy clusters, for example, are dense environments where galaxies are packed closely together. In the centers of clusters, galaxies frequently collide and merge, and the central galaxy, the brightest cluster galaxy, grows to enormous size by cannibalizing its neighbors. These brightest cluster galaxies are the most massive galaxies in the universe, often exceeding 1 trillion solar masses. They're red, elliptical, and completely dead, with essentially no star formation. They're the final resting place for all the galaxies that fell into the cluster and merged together over cosmic time. Galaxy mergers, then, are not just a way to shut down star formation. They're also a way to build the most massive galaxies in the universe and shape the large-scale structure of galaxy populations. But mergers aren't the only way that environment can affect a galaxy's evolution. There's another process particularly important in galaxy clusters that can strip gas away without requiring a collision at all. How Galaxies Die. Part 4. Environmental Effects. Imagine you're a small spiral galaxy, peacefully forming stars, minding your own business out in the field, the relatively empty regions between galaxy clusters. You have a nice reservoir of cold gas, a rotating disk, and a healthy star formation rate. Now imagine you fall into a galaxy cluster. Suddenly, you're not alone anymore. You're surrounded by hundreds or thousands of other galaxies, all moving at high speeds through a shared gravitational potential. And the space between those galaxies isn't empty. It's filled with hot gas, the intracluster medium, heated to tens of millions of degrees by the gravitational energy of the cluster itself. You're now moving through this hot gas at speeds of hundreds or even thousands of kilometers per second. And as you move, you feel a wind. Not a wind made of air, but a wind of hot plasma pushing against you. This is called ram pressure, and it's one of the most effective ways to strip gas from a galaxy. Ram pressure stripping works like this. As you move through the intracluster medium, the hot gas pushes against your cold gas, the gas in your disk that would normally form stars. If the pressure from that wind is strong enough, it can overcome your gravity and push the gas out of the disk entirely. The effect is strongest in the outer parts of the disk, where your gravity is weakest. The gas there gets swept away like leaves in the wind, forming long tails and streams behind you as you plow through the intracluster medium. Astronomers have observed this process in action in nearby galaxy clusters. There are beautiful images of galaxies with these long tails of gas being stripped away, tails that can extend for hundreds of thousands of light years. The galaxies look like comets, with heads of stars and tails of gas trailing behind them. And what happens to a galaxy that's been ram pressure stripped? It loses the raw material for making stars. Without cold gas, star formation shuts down. Over time, the galaxy fades from blue to red as the short-lived massive stars die and aren't replaced. What's left is a red and dead disk galaxy, still retaining its spiral structure, but completely quenched. These galaxies are sometimes called anemic spirals, because they look like normal spiral galaxies, but with much weaker star formation. They're the walking dead of the galaxy world, structurally intact, but no longer alive. Ram pressure stripping is most effective in the densest parts of galaxy clusters, near the center where the intracluster medium is hottest and thickest. Galaxies falling into the cluster from outside pass through a region of maximum ram pressure, and if they survive that passage without being completely stripped, they settle into orbits within the cluster, their gas depleted but their stars intact. But ram pressure isn't the only environmental effect that can kill a galaxy. There's also something called tidal stripping, or harassment. When galaxies pass close to each other, even if they don't actually merge, their mutual gravitational attraction can distort their shapes. Tidal forces pull on both galaxies, stretching them along the line connecting their centers. For a small galaxy passing by a much larger galaxy, the effect can be devastating. Stars and gas can be pulled out of the smaller galaxy entirely, forming tidal tails that eventually disperse into the cluster. This doesn't happen all at once, but over millions of years, over many close encounters with other galaxies, a small galaxy can be slowly whittled away, losing more and more of its material with each passage. Eventually, it might be reduced to a tiny remnant, a dwarf galaxy with very little gas and very few stars left. This process is called galaxy harassment, and it's particularly effective in rich galaxy clusters where galaxies are moving at high speeds and close encounters are frequent. There's also something called strangulation, or starvation. This is a more subtle effect. When a galaxy falls into a cluster, it's not just the gas in the disk that's affected. The galaxy is also surrounded by a large halo of diffuse gas, the circumgalactic medium we talked about earlier. That halo extends far beyond the visible galaxy, sometimes hundreds of thousands of light years. When the galaxy enters the cluster, the hot intracluster medium doesn't just strip the gas from the disk, it also strips the circumgalactic medium, removing the reservoir of gas that would normally fall inward and replenish the disk over time. So even if the disk itself isn't immediately stripped, the galaxy has lost its future supply of gas. It can keep forming stars for a while, using the gas that's already in the disk, but eventually that gas will be exhausted and there's nothing to replace it. This is strangulation. The galaxy doesn't die immediately. It dies slowly, starved of fresh gas, unable to sustain star formation over the long term. By the time its gas is depleted, it's been transformed into a red and dead system. All of these environmental effects work together in galaxy clusters. Ram pressure strips the disk gas. Tidal interactions disrupt the structure. Strangulation removes the halo gas. And if the galaxy happens to collide with another galaxy in the cluster, that can trigger a starburst that consumes whatever gas remains. The result is that galaxy clusters are graveyards. The central regions of clusters are dominated by red and dead galaxies, ellipticals and anemic spirals, with very little star formation. All the action, all the living galaxies still forming stars, they're out in the field, in the less dense regions where environmental effects are weaker. This is one of the clearest pieces of evidence that environment matters in galaxy evolution. If you plot star formation rate versus local galaxy density, you see a clear trend. Galaxies in dense environments form fewer stars than galaxies in low-density environments. The densest environments, the centers of galaxy clusters, have almost no star-forming galaxies at all. This is sometimes called the morphology density relation, or the star formation density relation, and it's been known for decades. But understanding the physical mechanisms behind it, understanding exactly how environment shuts down star formation, that's something astronomers are still working on. Because in reality, all these processes are happening at once. A galaxy falling into a cluster might experience Ram pressure stripping, tidal harassment, strangulation, and AGN feedback all at the same time. Disentangling which process is most important and under what conditions that requires detailed observations and sophisticated simulations. But what's clear is that environment is a major factor in determining whether a galaxy lives or dies. A galaxy's fate is not just determined by its internal properties, its mass, or its gas content, or its black hole. It's also determined by where it lives, what neighbors it has, and what forces it experiences from the surrounding universe. Galaxy death, it turns out, is as much about context as it is about content. Chapter 6. What dead galaxies look like. So, we've talked about how galaxies die. Now, let's talk about what they look like after they're dead. If you point a telescope at a dead galaxy, what do you see? The first thing you notice is the color. Dead galaxies are red. Not glowing red, not the red of an emission nebula where hydrogen gas is being ionized by young stars, but a dull orange red, the color of old stars. Why are old stars red? It comes down to their temperature. Stars emit light according to their surface temperature, and temperature determines color. Hot stars, with surface temperatures of tens of thousands of degrees, are blue or white. Cool stars, with surface temperatures of only a few thousand degrees, are red or orange. Massive stars are hot and blue, but they die quickly, within a few million years. Low-mass stars are cool and red, but they live for billions or even trillions of years. So, in a galaxy where star formation has shut down, where no new massive stars are being born, the blue stars disappear relatively quickly. What's left are the long-lived red and orange stars that formed long ago. The galaxy's light shifts toward the red end of the spectrum. Astronomers call this the red sequence, a tight correlation between galaxy mass and color. Massive dead galaxies are all roughly the same shade of red, slightly varying depending on their exact age and metallicity, but all clustering around that characteristic red color. If you look at a color magnitude diagram of galaxies, plotting their brightness against their color, you see two distinct populations. There's the blue cloud, galaxies that are still forming stars, and there's the red sequence, galaxies that have quenched. The boundary between them is sometimes called the green valley, a transitional region where galaxies are in the process of shutting down star formation. Galaxies don't stay in the green valley for long. Once quenching starts, it proceeds relatively quickly, and within a few 100 million years, the galaxy has moved from the blue cloud to the red sequence. So, color is the first clue that a galaxy is dead. But there are others. Dead galaxies tend to have very little dust. Dust in galaxies comes from dying stars, especially from the cool red giant stars that shed their outer layers in stellar winds. But dust doesn't last forever. It can be destroyed by shock waves, by radiation, by collisions with other dust grains. In an active star-forming galaxy, dust is constantly being produced and destroyed, and the production outpaces the destruction, so there's always a reservoir of dust present. But in a dead galaxy where star formation has stopped, dust production slows down dramatically. The dust that's already there gradually gets destroyed, and over a few 100 million years, the galaxy becomes relatively dust-free. You can see this in infrared observations. Dust absorbs starlight and re-emits it as infrared radiation. Star-forming galaxies glow brightly in the infrared because of all the warm dust heated by young stars. Dead galaxies are faint in the infrared. There's just not much dust there to emit. Dead galaxies also have very little molecular gas. Remember, molecular clouds are the sites of star formation. If there's no star formation, there's probably no molecular gas, or at least not enough to make a difference. Astronomers can detect molecular gas through radio observations, looking for emission from carbon monoxide molecules, which are a good tracer of molecular hydrogen. When they point radio telescopes at dead galaxies, they see very little emission. The gas is gone. But here's something interesting. Dead galaxies often do have some atomic hydrogen gas. Not a lot, but a detectable amount. Atomic hydrogen is more diffuse and harder to collapse into stars than molecular hydrogen. So you can have a galaxy with some atomic hydrogen remaining, but not enough dense molecular gas to form stars. This atomic hydrogen might be left over from the quenching process, or it might be accreted from the surroundings after the galaxy was quenched. Either way, its presence shows that dead doesn't necessarily mean completely gas-free. It just means gas poor enough that star formation can't sustain itself. Now, let's talk about morphology, the shape and structure of dead galaxies. The most common morphology for a dead galaxy is elliptical. Elliptical galaxies are smooth and featureless, with no spiral arms, no disk structure, just a roughly egg-shaped or spherical distribution of stars. They range in shape from nearly spherical, called E0 galaxies, to highly elongated, called E7 galaxies. Ellipticals are dominated by old stars. They have very little gas and dust, and they have almost no star formation. They're the quintessential dead galaxies. But not all dead galaxies are ellipticals. Some are what astronomers call S0, or lenticular galaxies. These have a disk-like spiral galaxies, but no spiral arms and very little gas. They're sort of intermediate between spirals and ellipticals, structurally. They have a bulge and a disk, but the disk is smooth and featureless. S0 galaxies are common in galaxy clusters, and they're thought to be the result of environmental processes like RAM pressure stripping. A spiral galaxy falls into a cluster, its gas is stripped away, star formation shuts down, but the disk structure remains. What's left is an S0, a dead disk galaxy. There are also dead spiral galaxies, sometimes called red spirals or passive spirals. These are rarer, but they exist. They still have spiral arms, you can see the structure clearly, but the arms are not lit up by young blue stars. Instead, they're traced by older stars, and there's very little ongoing star formation. How do you create a dead spiral? Probably through strangulation. The galaxy's halo gas is removed, so it can't replenish the disk, but the disk itself isn't violently disrupted. Star formation gradually declines as the existing gas is used up, but the structure remains intact. So there's diversity among dead galaxies, just as there's diversity among living ones. But there are common features. Red color, low dust content, little or no molecular gas, and low or zero star formation rate. Astronomers have various ways to measure star formation rate. One common method is to look for ultraviolet emission, which comes from hot young stars. Star-forming galaxies are bright in ultraviolet. Dead galaxies are faint. Another method is to look for emission lines in the galaxy's spectrum, particularly the H-alpha line, which comes from hydrogen gas being ionized by ultraviolet radiation from massive stars. If you see strong H-alpha emission, the galaxy is forming stars. If H-alpha is absent or very weak, star formation has shut down. A third method is to look in the far infrared, detecting the thermal emission from dust heated by young stars. Again, star-forming galaxies are bright, dead galaxies are faint. All these methods converge on the same conclusion. Dead galaxies have star formation rates close to zero, typically less than 1 solar mass per year, often much less. For comparison, the Milky Way forms about 7 solar masses per year. Some starburst galaxies form thousands of solar masses per year. So dead galaxies are at the extreme low end of the star formation scale. Now, when astronomers look at the population of galaxies in the universe, they find that about half of all massive galaxies are dead. Not all galaxies, but specifically massive galaxies, those with masses above about 10 to the power of 11 solar masses, or 100 billion solar masses. Less massive galaxies are much more likely to still be forming stars. Small galaxies, dwarf galaxies, they're almost all on the blue cloud, still active. It's the big galaxies that are most likely to be dead. Why is that? It probably has to do with black hole feedback. Massive galaxies have massive black holes. and massive black holes can generate more powerful feedback, shutting down star formation more effectively. Small galaxies have small black holes, and their feedback is weaker, less able to completely quench star formation. But environment also plays a role. Massive galaxies are more likely to live in galaxy clusters, where environmental effects can shut down star formation. Small galaxies are more likely to live in the field, where they're relatively isolated and can keep forming stars for longer. So the picture that emerges is one where galaxy death is more common among massive galaxies in dense environments, and less common among small galaxies in isolated regions. But it's not absolute. There are massive galaxies that are still forming stars, and there are small galaxies that have quenched. The trends are statistical, not universal. And there's one more thing I want to mention about dead galaxies. They're not static. They're not frozen in time. They continue to evolve even without star formation. The stars in a dead galaxy are still orbiting the center. They're still interacting gravitationally with each other. Over time, those interactions cause the galaxy to evolve dynamically. Stars can be scattered to higher or lower orbits. The galaxy can become more or less concentrated toward the center. If it's part of a cluster, it can undergo tidal interactions with other galaxies, losing stars to the cluster's tidal field. And very rarely, a dead galaxy can come back to life. If it accretes fresh gas from the surroundings, or if it merges with a gas-rich galaxy, star formation can resume. The galaxy can move back from the red sequence to the blue cloud. This is rare, but it happens. And it shows that galaxy death is not always permanent. Let's talk about that possibility in the next chapter. Chapter 7. Can dead galaxies come back to life? The universe is full of surprises. And one of the surprising things astronomers have discovered in recent years is that some dead galaxies can be resurrected. Galaxy death is not always a one-way street. Now, let me be clear. Most dead galaxies stay dead. Once a massive elliptical galaxy is quenched, once it's settled into a stable configuration with very little gas and no star formation, it's unlikely to ever become a vigorous star-forming galaxy again. The conditions that shut it down in the first place, whether that's black hole feedback or environmental effects or simple lack of gas, those conditions usually persist. But there are exceptions. There are scenarios where a dead galaxy can acquire new gas and resume star formation, at least temporarily. Let's go through them. The first scenario is gas accretion from the cosmic web. Remember, galaxies are embedded in vast halos of diffuse gas, the circumgalactic medium. That gas is constantly being replenished by infall from the larger-scale cosmic web, the network of filaments that connects galaxies across the universe. In the early universe, this infall was rapid and continuous. But even in the modern universe, it still happens, just at a slower rate. If a dead galaxy is positioned at the intersection of cosmic web filaments, or if it's in an environment where there's still a significant reservoir of cool gas available, it might be able to accrete that gas and restart star formation. This is most likely to happen in relatively isolated galaxies, field galaxies that aren't part of dense clusters. In clusters, the intracluster medium is too hot, and any cool gas that tries to fall in gets heated or stripped away. But in the field, especially in regions that are slightly underdense compared to the average, there can still be streams of cold gas funneling into galaxies. If enough gas accumulates, if it can cool and settle into the disk, star formation can begin again. The galaxy moves back toward the blue cloud. It's been rejuvenated. The second scenario is a minor merger with a gas-rich dwarf galaxy. Even though major mergers between large galaxies tend to shut down star formation, minor mergers, where a small gas-rich galaxy is absorbed by a larger one, can actually do the opposite. The small galaxy brings its gas with it. When it merges with the larger galaxy, that gas settles into the disk and can trigger new star formation. The amount of star formation depends on how much gas the dwarf galaxy had, but in some cases it can be enough to move the galaxy from the red sequence back toward the blue cloud, at least temporarily. Minor mergers are fairly common. Large galaxies are constantly accreting small satellite galaxies. The Milky Way is doing it right now. And each time a satellite is accreted, there's a chance it will bring some gas with it and trigger a burst of star formation. For a massive dead elliptical galaxy, a minor merger with a dwarf probably won't fully rejuvenate it. The amount of gas is just too small compared to the galaxy's total mass. But it can create localized pockets of star formation, small blue regions within an otherwise red galaxy. Astronomers sometimes see these, and they're evidence of recent gas accretion, probably from a minor merger. The third scenario is environmental changes. A galaxy that was quenched by environmental effects, like ram pressure stripping in a galaxy cluster, might be able to recover if it's later removed from that environment. Imagine a galaxy that fell into a cluster and had its gas stripped away. It's now a red and dead S0 galaxy orbiting within the cluster. But then, through some gravitational interaction, maybe a close encounter with another galaxy or a cluster merger event, it gets ejected from the cluster. It's flung out into the field, into a lower density environment where environmental effects are much weaker. If the galaxy can then accrete fresh gas from the cosmic web or from minor mergers, star formation could resume. The galaxy would have a second chance at life. This scenario is probably rare because it requires a very specific set of circumstances. But simulations suggest it can happen, and observers have found some examples of galaxies that seem to be in the process of rejuvenation after being ejected from clusters. The fourth scenario involves the central black hole. We talked earlier about how black hole feedback can shut down star formation by heating the gas. But black hole activity is not constant. It fluctuates over time, depending on how much gas is available for accretion. If the black hole runs out of gas to accrete, its activity drops. The heating stops. The gas in and around the galaxy starts to cool again. And if conditions are right, that cooling gas can collapse and form new stars. This might happen in cycles. The gas cools and starts to form stars. That brings more gas toward the center. The black hole starts accreting again. Its feedback heats the gas and shuts down star formation. Accretion slows down. The black hole becomes less active. The gas cools again. and the cycle repeats. There's evidence for this kind of cyclical activity in some galaxies, especially in galaxy clusters. The central galaxy shows signs of recent star formation, small pockets of young stars, but embedded in a much larger population of old stars. This suggests rejuvenation, but only partial and temporary. Now, I want to emphasize that all of these rejuvenation scenarios are exceptions, not the rule. The vast majority of dead galaxies stay dead. Once a galaxy has quenched, especially if it's a massive galaxy in a dense environment, the chances of it coming back to life are very small. But the fact that it can happen at all is important. It tells us that galaxy evolution is not strictly linear. Galaxies don't just march along a single path from birth to death. They can backtrack. They can have multiple episodes of star formation and quenching. Their histories can be complicated and messy. And when we try to understand the galaxy population as a whole, when we try to build theoretical models that explain why some galaxies are blue and some are red, we need to account for these complications. We need to include the possibility of rejuvenation, even if it's rare. There's a term astronomers use for this. They call it frosting. Imagine a red and dead elliptical galaxy as a cake. The bulk of the cake is made of old stars, formed long ago and now faded to red. But on top of the cake, there's a thin layer of frosting, a small population of young blue stars formed recently through gas accretion or a minor merger. The frosting doesn't change the overall nature of the galaxy. It's still predominantly old and red. But it adds a bit of complexity, a bit of recent activity. And when you're trying to measure properties like star formation rate or stellar age, that frosting can make a difference. Some astronomers argue that many, maybe even most red sequence galaxies have at least a little bit of frosting. They're not completely dead. They're mostly dead, but with a tiny amount of residual star formation happening somewhere within them. If that's true, then the red sequence is not as cleanly defined as we might think. There's a gradation between fully active star-forming galaxies and completely dead galaxies, with a whole range of partially quenched systems in between. And this has implications for how we think about galaxy evolution. Instead of thinking about two distinct populations, the living and the dead, maybe we should think about a continuum, with galaxies moving back and forth along that continuum depending on their circumstances. But even if rejuvenation is possible, even if some dead galaxies can come back to life, the overall trend is clear. Star formation in the universe is declining. More and more galaxies are quenching. Fewer and fewer galaxies are forming new stars at high rates. The universe is aging. And one day, billions of years from now, our own galaxy will age too. Let's talk about the future of the Milky Way. Chapter 8. The Future of the Milky Way. Right now, as you listen to these words, the Milky Way galaxy is alive. Stars are forming in molecular clouds scattered throughout the disk. Massive stars are exploding as supernovae, enriching the interstellar medium with heavy elements. Gas is flowing in from the cosmic web, replenishing the supply of star-forming material. Our galaxy is active, vibrant, full of light and motion and change. But it won't always be this way. The Milky Way's future has been written in the stars, or more accurately, in the trajectories of the galaxies around us. And that future involves a collision. The Andromeda Galaxy, also known as Messier 31 or M31, is the nearest large galaxy to the Milky Way. It's a spiral galaxy, much like our own, maybe slightly larger, with about 1 trillion solar masses of stars. And it's moving toward us at about 110 kilometers per second. Now, before you panic, let me assure you that we have plenty of time. Andromeda is currently about 2.5 million light-years away. At its current speed, it will take about 4 to 5 billion years to reach us. But reach us it will. The collision is inevitable. Gravity has decreed it. When the Milky Way and Andromeda collide, it will be a spectacular event. Remember, the stars are so far apart that they won't actually hit each other. But the gravitational interactions will be dramatic. The two galaxies will pass through each other, their disks interpenetrating, their stars sloshing back and forth like water in a disturbed pool. The first pass will distort both galaxies. Tidal forces will stretch and warp their disks. Long tidal tails of stars and gas will be pulled out, arcing away into intergalactic space. The galaxies will look highly disturbed, chaotic, nothing like the elegant spirals they are now. But gravity won't let them escape. After the first pass, they'll slow down, stop, and fall back together for a second collision. And a third, and a fourth. Each collision will remove more orbital energy, bringing them closer together. During these collisions, something else will happen. The gas clouds in both galaxies will slam together, and those collisions will trigger intense star formation. The Milky Way and Andromeda will become starburst galaxies, forming new stars at rates perhaps 10 or 20 times their current rate. The night sky, if anyone is around to see it, will be ablaze with brilliant blue stars, glowing nebulae, and the light from millions of newly formed star clusters. But this burst of star formation will be brief, cosmically speaking. Within a few 100 million years, most of the gas will be consumed. Either it will be converted into stars, or it will be heated and ejected by the combined supernovae and stellar winds from all those massive young stars. And gradually, over about 1 billion years after the initial collision, the two galaxies will merge completely. Their stars will mix together into a single system. The two supermassive black holes at their centers will spiral inward and eventually merge, releasing a burst of gravitational waves. What emerges from this merger will no longer be a spiral galaxy. It will be an elliptical galaxy, a smooth, featureless ellipsoid of stars. Astronomers have already given it a name, Milkomeda, or sometimes Milk-Dromeda. And Milkomeda will be a dead galaxy. It will have consumed most of its gas during the merger. What little gas remains will be too hot to form stars, heated by the feedback from the central black hole and by the residual energy from the starburst. Star formation will drop to nearly zero. The galaxy will fade from blue to red over the next few 100 million years as the short-lived massive stars die and only the long-lived low-mass stars remain. Milkomeda will join the red sequence, the Milky Way's death. Now, I want to put this in perspective. 4 to 5 billion years is a very long time. The Sun has been around for about 4.6 billion years, so the Andromeda collision will happen roughly as far in the future as the formation of the Sun is in the past. Humanity, if we're still around, will have had billions of years to prepare. And honestly, the collision itself won't be dangerous. Remember, the stars are too far apart to collide. The Sun and the solar system will just be gently perturbed, ending up in some new orbit within Milky Way. There is one potential concern, though. When the two central black holes merge, they'll release a burst of gravitational waves. If any star system happens to be very close to the merging black holes at that moment, it could be gravitationally disrupted and ejected from the galaxy entirely. But the odds of that happening to the solar system specifically are vanishingly small. More likely, the Sun and Earth will just find themselves in a new galaxy, orbiting peacefully, unaware that anything dramatic has happened on the scale of the galaxy as a whole. But what about after the merger? What will Milky Way be like as a dead galaxy? Well, it will still be full of stars. All the stars from the Milky Way and Andromeda will still be there, now mixed together. That's about 2 trillion stars total, maybe more. And most of those stars will continue shining for billions or tens of billions of years. The Sun will still be there, though by then it will be nearing the end of its main sequence lifetime. In about 5 billion years, the Sun will begin to evolve into a red giant, expanding to engulf the inner planets, possibly including Earth. But that's a separate issue from the Andromeda collision. It's going to happen regardless. Other stars will continue their normal life cycles. Low-mass stars will keep burning steadily for trillions of years. Medium-mass stars will evolve into red giants, shed their outer layers, and become white dwarfs. Massive stars, if any remain from the recent starburst, will explode as supernovae. But no new stars will form to replace the ones that die. The population of stars in Milky Way will slowly decline as stars exhaust their fuel and fade away. Over tens of billions of years, the bright blue and white stars will all die out. Then the yellow stars like the Sun. Eventually, only the red dwarfs will remain, the smallest and coolest stars, the ones that can burn hydrogen for trillions of years. Milky Way will become dimmer and dimmer, redder and redder, as its stellar population ages and dies. And billions of years after that, even the red dwarfs will start to fade. They'll exhaust their hydrogen fuel and cool into brown dwarfs. Objects too small to sustain fusion, slowly radiating away their residual heat until they become cold, dark, invisible. By the time the universe is 100 trillion years old, Milky Way will be a ghost galaxy. A vast collection of stellar remnants, white dwarfs and neutron stars and black holes, all orbiting in darkness around the central supermassive black hole. This is the eventual fate of all galaxies. Not just the Milky Way and Andromeda, but every galaxy in the universe. They all follow the same path: birth, life, death, and then a long, slow fade into darkness. But let's not get too far ahead of ourselves. Let's talk about what happens to the universe as a whole in the deep future. Chapter 9. The long-term fate of the universe. We've talked about the death of individual galaxies, Now let's zoom out and look at the big picture. What happens to the universe as a whole as galaxies die and star formation declines? To understand the future, we first need to understand the present. Right now, the universe is 13.8 billion years old. It's been expanding since the Big Bang, and observations show that the expansion is actually accelerating, driven by a mysterious component called dark energy. We don't know what dark energy is. We just know it's there because we can see its effects. It's pushing the universe apart, making the expansion faster and faster over time. And it makes up about 68% of the total energy density of the universe. Another 27% is dark matter, the invisible stuff that provides the gravitational scaffolding for galaxy formation. And only about 5% is ordinary matter, the stuff that makes up stars and planets and people. Given that distribution, and given the accelerating expansion, what does the future hold? Well, the first thing to understand is that galaxies will become more and more isolated. As the universe expands, the space between galaxy clusters grows. Clusters that are currently close together will drift apart. Eventually, they'll be so far apart that light from one cluster can't even reach another, because the space between them is expanding faster than the speed of light. This is called the cosmic event horizon. It's the distance beyond which objects are receding from us so fast that their light can never reach us, no matter how long we wait. As the universe ages, the cosmic event horizon shrinks. Fewer and fewer galaxies remain visible. Eventually, in the far future, an observer in one galaxy will only be able to see their own galaxy and maybe the members of their local galaxy cluster. Everything else will have receded beyond the cosmic event horizon. The universe will appear much emptier than it does now. But let's focus on what happens within a single galaxy cluster, like the local group that will eventually merge into Milky Way. Star formation will continue for a while, but at a declining rate. As we've discussed, the supply of gas is finite, and it's being consumed by star formation and lost through feedback processes. Over tens of billions of years, galaxies will run out of gas. By the time the universe is about 100 billion years old, about 7 times its current age, star formation in most galaxies will have ceased entirely. There might be a few isolated pockets where gas is still collapsing into stars, but on average, across the universe, star formation will have dropped to essentially zero. At that point, the universe enters what astronomers call the degenerate era, the era dominated by stellar remnants rather than active stars. The most common objects will be white dwarfs, the remnants of low and medium mass stars. These are incredibly dense objects, about the size of Earth, but with a mass similar to the Sun. They no longer undergo fusion. They just slowly radiate away their residual heat, cooling over trillions of years. There will also be neutron stars, the remnants of more massive stars, even denser than white dwarfs, about the size of a city, but with masses of 1 to 2 times the Sun. And black holes, the remnants of the most massive stars, objects so dense that not even light can escape their gravity. But even though fusion has stopped, there's still some activity in the degenerate era. White dwarfs can collide with each other or accrete matter from companion stars. If a white dwarf's mass grows beyond a critical limit, about 1.4 times the mass of the Sun, it becomes unstable and explodes as a Type I supernova. These supernovae will continue to happen, scattered randomly throughout the dead galaxies, providing brief flashes of light in an otherwise dark universe. There's also the possibility of new stars forming, at least for a while. If two brown dwarfs collide and merge, they might reach the mass threshold for hydrogen fusion and become a red dwarf star. These collisions will be rare, but over trillions of years they'll happen occasionally. So the degenerate era won't be completely dark, but it will be much, much dimmer than the universe today. Most stars will be gone. Most of the light will come from the fading glow of white dwarfs and the occasional supernova. And this era will last a very long time, trillions upon trillions of years. Because white dwarfs cool very slowly and the lowest mass red dwarf stars can burn hydrogen for up to 10 trillion years. But eventually, even these stars will fade. By the time the universe is 10 to the power of 14 years old, 100 trillion years old, the last red dwarf will exhaust its fuel. The last white dwarf will cool to the temperature of the cosmic microwave background radiation and stop emitting detectable light. The universe will have entered the black dwarf era, named after the cold, dark stellar remnants that will dominate it. At this point, galaxies will be invisible. They'll still be there, their stars replaced by black dwarfs and neutron stars and black holes, all still orbiting under gravity, but emitting no light. The only sources of light will be extremely rare events. A black dwarf colliding with another black dwarf, releasing a brief burst of energy. A star being torn apart by a black hole, creating a temporary accretion disk. Matter falling into a supermassive black hole, perhaps because two black dwarfs collided near the galactic center and one got kicked inward. These events will be few and far between, separated by millions or billions or trillions of years. And then, on even longer timescales, the galaxies themselves will start to evaporate. This is a process called gravitational relaxation. In a galaxy, stars are constantly passing by each other, interacting gravitationally. Most of these interactions are gentle, just slightly changing each star's orbit. But occasionally, a close encounter can give one star a large boost in velocity. If that boost is large enough, the star can reach escape velocity and be ejected from the galaxy entirely. Over time, through countless gravitational interactions, galaxies will slowly lose stars to this evaporation process. The timescale for a galaxy to lose a significant fraction of its stars this way is about 10 to the power of 19 years, 10 billion years. By that time, most galaxies will have evaporated, their stars scattered into intergalactic space. What's left behind is the central supermassive black hole, maybe with a few tightly bound stars orbiting close to it. And then, on even longer timescales, something truly remarkable happens. Protons decay. Now, this is theoretical. We've never observed proton decay, and there are strict experimental limits on how fast it can happen. But many theories of particle physics predict that protons are not stable forever. They can decay into lighter particles, photons and positrons and neutrinos, with a half-life of maybe 10 to the power of 34 years. If proton decay happens, then all ordinary matter, everything made of atoms, will eventually disintegrate. Black dwarfs will slowly evaporate, their protons decaying one by one, releasing tiny flashes of energy as they go. By the time the universe is 10 to the power of 40 years old, all protons will have decayed. Ordinary matter as we know it will no longer exist. All that's left are black holes and the particles they emit. But even black holes don't last forever. Stephen Hawking showed in the 1970s that black holes emit radiation through a quantum process now called Hawking radiation. They emit particles and photons very slowly, very gradually, and as they emit, they lose mass. A black hole of stellar mass, a few times the mass of the Sun, will take about 10 to the power of 67 years to evaporate through Hawking radiation. A supermassive black hole, like the one at the center of the Milky Way, will take about 10 to the power of 100 years. But eventually they too will evaporate, disappearing in a final burst of radiation. And when the last black hole has evaporated, when there's nothing left but a thin soup of photons and neutrinos and other fundamental particles spreading through an ever-expanding universe, we reach what's called the dark era, or sometimes the photon era. This is the ultimate fate of the universe, at least according to our current understanding. An infinite void, ever-expanding, ever-cooling, ever-darker, with nothing but the faintest whisper of radiation left over from the glorious galaxies and stars that once filled it with light. This is the heat death of the universe, the final thermodynamic equilibrium, the state of maximum entropy. And it's not a violent end. It's not a dramatic collapse or a catastrophic explosion. It's just a slow, quiet fading into darkness. From the cosmic perspective, galaxy death is not the end of the story. It's the middle chapter. The end is much farther away, much stranger, much more profound. But let me be clear. These are timescales so vast as to be almost meaningless. 10 to the power of 100 years is a 1 followed by 100 zeros. To put that in perspective, the universe has existed for only about 10 to the power of 10 years. 10 billion years. We're talking about a future that is 10 to the power of 90 times longer than the universe has already existed. No human mind can truly grasp such spans of time. They're beyond comprehension. And there's always the possibility that our understanding is incomplete. Maybe there's new physics we don't know about. Maybe the universe will behave differently than we predict. Maybe there are processes that can generate new stars or new galaxies even after the ones we see now have died. We're extrapolating from our current knowledge, but that knowledge is limited. The universe has surprised us before, and it will surely surprise us again. But based on what we know now, this is the most likely scenario. The universe will age, stars will die, galaxies will quench, and eventually, after an almost incomprehensible span of time, even the black holes will evaporate, leaving nothing but darkness. It's a sobering thought, but it's also, in its own way, beautiful, because it reminds us how precious and rare our moment is. We live in an era when the universe is alive, with stars, when galaxies are still forming, when light still fills the cosmos. This golden age won't last forever, but it's happening now, and we're here to witness it. Conclusion: a quiet ending. We started this journey by asking a simple question: how do galaxies die? And what we've discovered is that the answer is anything but simple. Galaxies die in many different ways. They run out of gas, starving themselves of the raw material for making stars. They're killed by their own central black holes, which heat the gas and prevent it from collapsing. They collide with other galaxies, triggering starbursts that consume all the available fuel. They're stripped of their gas by the environment, by ram pressure and tidal forces in galaxy clusters. Each of these processes operates on different timescales, in different environments, and for different types of galaxies. And often, multiple processes work together, each contributing to the eventual quenching of star formation. Galaxy death is not a single phenomenon. It's a collection of related phenomena, all with the same end result: the cessation of star formation, the fading from blue to red, the transformation from a living, vibrant system to a quiet, passive relic. And it's not instantaneous. It takes hundreds of millions of years, sometimes billions of years, for a galaxy to fully quench. During that transition, the galaxy passes through the Green Valley, that intermediate state where star formation is declining, but not yet zero. Some galaxies die violently, in starbursts and mergers, and powerful outflows driven by black holes or supernovae. Others die slowly, gradually using up their gas over billions of years without any dramatic events. And a rare few, can come back to life, at least temporarily, if they manage to accrete fresh gas from their surroundings. But the overall trend is clear. The universe is aging. Star formation peaked about 10 billion years ago at cosmic noon, and it's been declining ever since. More and more galaxies are joining the red sequence. Fewer and fewer galaxies are forming stars at high rates. In the deep future, billions of years from now, star formation will cease entirely. The last stars will form, burn, and die. The universe will fade from the vibrant place we see today into a cold, dark expanse filled with stellar remnants. This is not a fate we need to fear. It's simply the natural progression of cosmic evolution, the inevitable consequence of the laws of physics and the finite supply of gas in the universe. And in a strange way, it makes our own moment in cosmic history all the more precious. We live in a universe that still sparkles with starlight, where nebulae glow in brilliant reds and blues, where galaxies span the sky in elegant spirals and majestic ellipses, where new stars are born every day and supernovae explode in spectacular displays of light and energy. This won't last forever, but it's happening now, in our time, and we're fortunate enough to be here to see it. The Milky Way, our home galaxy, is still alive, still forming stars, still evolving. Yes, it will one day collide with Andromeda and transform into Milky Way, a dead elliptical galaxy. And billions of years after that, even Milky Way will fade as its stars exhaust their fuel and die. But that's billions of years away. For now, we live in a galaxy that's in its prime, forming new stars, cycling matter through generation after generation of stellar evolution, creating the heavy elements that make up planets and people and everything we know. We are, quite literally, made of stars. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of it was forged in the cores of massive stars that lived and died before the sun even formed. Those stars blasted their enriched material back into the interstellar medium, where it eventually collapsed to form new stars and planets, including our solar system. And when the sun dies, billions of years from now, some of that material will be recycled once again, contributing to future generations of stars, at least until the Milky Way runs out of gas and quenches entirely. We're part of a cosmic cycle, a grand recycling of matter and energy that spans billions of years and connects us to the very origins of the universe. Galaxy death is one phase of that cycle. It's the moment when the recycling stops, when the cycle breaks down, when no new stars are born to carry the process forward. It's an ending, yes, but it's also a completion. A galaxy that has quenched has reached the end of its productive life. It's created all the stars it's going to create. It's synthesized all the heavy elements it's going to synthesize. It's done its part in the cosmic story. And now it can rest, slowly fading over billions and trillions of years. Its stars, one by one, reaching the ends of their lives, until nothing remains but cold, stellar remnants orbiting in darkness. It's a quiet ending, not a bang, but a whisper, and maybe that's appropriate, because the universe itself began with a bang, the Big Bang, that violent birth of space and time and matter and energy. But it will end with a whisper, a slow fade into darkness as the stars die out and the galaxies go cold. From chaos to order, from light to darkness, from birth to death. That's the story of the universe. And galaxy death is a crucial chapter in that story, the moment when individual galaxies make the transition from active participants in cosmic evolution to passive relics of a more vibrant era. But here's the thing, even a dead galaxy has a story to tell. When astronomers look at elliptical galaxies, those smooth, red, featureless systems, they're not just seeing dead galaxies, they're seeing history. They're seeing the fossil record of galaxy formation and evolution, preserved in the distribution and motions of billions of stars. By studying the stars in an elliptical galaxy, by measuring their ages and chemical compositions and orbital properties, astronomers can reconstruct what that galaxy went through in its past. Was it formed by a major merger? Did it accrete many small satellites over time? When did it quench? How rapidly did star formation shut down? Dead galaxies are not boring. They're archives, they're libraries. They contain information about the universe's past, information that's been preserved for billions of years, waiting for us to decipher it. And the same will be true of Milkomeda, the future merger remnant of the Milky Way and Andromeda. When Milkomeda has fully quenched, when it's been a red and dead elliptical for billions of years, the stars within it will still carry the memory of the Milky Way and Andromeda as they were. The chemical fingerprints of stellar populations, the orbital patterns inherited from the merger, the ages of star clusters formed during the starburst. all of that information will remain encoded in the stars, a testament to the galaxies that came before. So, galaxy death is not erasure. It's transformation. It's the conversion of a dynamic, evolving system into a static, stable configuration that preserves the history of that evolution. And on the grandest scales, galaxy death is part of the universe's journey from its hot, dense, uniform beginning to its cold, diffuse, structured ending. The Big Bang created a universe filled with hydrogen and helium, evenly distributed, with only the tiniest variations in density from place to place. Gravity amplified those variations, pulling matter together into stars and galaxies. Stars fused hydrogen and helium into heavier elements and returned those elements to space when they died. Galaxies grew through mergers and gas accretion, becoming larger and more complex. And now, as the universe ages, galaxies are shutting down, one by one, locking up their matter in long-lived stars and stellar remnants. Eventually, all the gas will be gone. All of the stars will have formed. The universe will have reached a state where no further star formation is possible. And from that point forward, it's just a slow decay. Stars dying, white dwarfs cooling, galaxies evaporating, black holes radiating away their mass. Until, at the end of time, if there is such a thing, there's nothing left but a cold, dark, empty universe, forever expanding, forever cooling, forever fading. That's the ultimate consequence of galaxy death. Not just the death of individual galaxies, but the death of the entire universe's ability to create light and structure and complexity. It's a melancholy thought, but it's also, in a strange way, comforting, because it means the universe has a story. It has a beginning, a middle, and an end. It's not eternal and unchanging. It's dynamic and evolving. And we, here in the middle chapters, get to witness and understand that evolution. We get to see galaxies as they live and die. We get to study the processes that shape them. We get to peer into the past through our telescopes and see what galaxies looked like billions of years ago, when the universe was younger and more active. And we get to look into the future through our simulations and theories and predict what will happen billions of years from now. We're living in a remarkable time, a time when we have the tools and the knowledge to understand the universe on the largest scales, to trace its history from the Big Bang to the present and beyond, to see ourselves as part of a cosmic story that spans 13.8 billion years of past and trillions upon trillions of years of future. And galaxy death, the subject of this entire exploration, is a crucial part of that story. It's the transition from the universe's active star-forming phase to its passive, quenched phase. It's the moment when galaxies stop creating new light and begin their slow fade into darkness. It's the end of one era and the beginning of another. And it's happening right now, all around us, as we watch through our telescopes and try to understand. So, the next time you look up at the night sky, at the faint smudge of the Andromeda Galaxy or the scattered stars of our own Milky Way, remember this. You're looking at living galaxies, galaxies in the prime of their lives, still forming stars, still evolving, still vibrant with light and energy. But you're also looking at galaxies with a finite lifespan. Galaxies that will one day die, just as surely as individual stars and planets and people die. And when they do, when the last star forms and the last supernova explodes and the last stellar remnant cools to the temperature of space, the universe will enter a new phase, quieter, darker, emptier. But until then we have this. We have galaxies full of stars. We have light streaming across the cosmos. We have the ongoing drama of cosmic evolution, playing out on scales of space and time that dwarf our everyday experience, but that we can still observe, study, and comprehend. We have the privilege of living in a universe that's still alive, and that's something worth appreciating while it lasts. Thank you for joining me on this journey through the life and death of galaxies. I hope you've gained a deeper appreciation for these magnificent structures, for the processes that create and destroy them, and for our place in the grand cosmic story. The universe is vast and ancient and beautiful, and we're lucky to be here in this moment to witness its glory, even as we know that glory won't last forever.